Thank you. Good morning, everyone. I have nothing to disclose. So this morning I'm going to try to give you a very broad overview of MRI physics, speaking primarily in the classical sense. And so I'm going to try and cover a number of different topics very quickly. And then hopefully throughout the rest of this course you'll have a chance to dive into some of these topics a little bit more. And then at the end, I'll spend a few slides just putting it all together in the form of pulse sequences, which is the practical way we use these techniques on a daily basis, and talking about block equations, which is a really helpful tool for us to understand the classical description of MRI physics. So I'm going to start with this compass needle analogy, and this is a very simplified analogy, but I think it's helpful to get us started into some of the MRI physics concepts. So we all know a compass needle is a tiny magnet, and if we put it near a big magnetic field, it's going to rotate to point towards that magnetic field. So watch what happens when we put a magnetic field in place. The compass needle rotates, and then it oscillates as it settles into an equilibrium position. And that frequency that it oscillates at, we can think of as the resonant frequency. So if we wanted to now displace this compass needle from its equilibrium position, we could give it a tiny push with a second, smaller magnet. But the best way, the way we're going to get the most response, is by oscillating this small magnet at a particular frequency, that same resonant frequency, so that with these tiny pushes, we move the compass needle from its equilibrium position. We could think of this moving magnet instead as an electromagnetic field. And of course, because the compass needle itself is a tiny magnet, it will produce its own field that we can measure. And so this is a really simplified example, but we use a lot of these concepts in MRI physics. And so in MRI, we are imaging nuclei, and we're imaging a particular type of nuclei that have a property called spin. And so if we think specifically about hydrogen nuclei, which is what we image the most, we know that this is positively charged. And so we can think of the nuclei as a spinning sphere of charge, which looks a lot like a current loop. And so the physicists in the room will know that if we have a current loop, we then have a magnetic moment. And so each of these little nuclei is acting as a little bar magnet in the body, and that's what we're using to generate our MRI signal. So there are two things that happen when we place these nuclei into a magnetic field. The first is that the spins tend to align either with or against the static magnetic field. And because they have an angular momentum and they're experiencing this magnetic force, they start to precess around the field. And the frequency of this precession is very well defined, and this is the Larmoire frequency. And this frequency is proportional to both the gyromagnetic ratio, which is specific to the nuclei, and to the external magnetic field. And this frequency, which is both our precessional frequency and our resonance frequency. So if we think again about hydrogen, we can look at the gyromagnetic ratio and extend this to look at the Larmoire frequencies for the range of field strengths that most people in this room probably use. And so we look at the Larmoire frequencies, and you'll notice that all of these are in the radio frequency band, which is why in MRI jargon we often refer to radio frequency or RF pulses. In the body, of course, we have lots of water molecules, so this gives us lots of hydrogen nuclei to image. So we can think of all these water molecules as being made up of many spins. And in reality, they can be treated as an ensemble, so we don't need to consider each spin individually, but we treat them as an ensemble. So here I'm showing an example of many spins spinning as a giant disco ball, and they're all precessing at the Larmoire frequency. They're distributed along the surface of a sphere, although they're oriented either parallel or anti-parallel to the main magnetic field. And a few more protons per million are aligned parallel to the magnetic field compared to anti-parallel. And this excess is given by the Boltzmann distribution. And so when we sum up all of these magnetic moments, we get a net magnetization. And this net magnetization is pointed in the same direction as the main magnetic field. Conventionally, that is the Z direction. And we're at a stage now where we can start to stop thinking about the protons and instead just think about this net magnetization and start to manipulate that net magnetization to create an image. So going back to this compass needle example, we were able to disturb the compass needle from its equilibrium position using an electromagnetic field. So in MRI, we do that using a second magnetic field, which we refer to as our B1 field. And this is a time-varying magnetic field. It's circularly polarized, which means that it's rotating in the transverse plane, or the XY plane, at the Larmoire frequency. And so because it's rotating at the Larmoire frequency, it causes changes in energy state on a quantum mechanical level, and on a macroscopic scale, it causes that net magnetization vector to tip away from its equilibrium position and start to slowly rotate down into the transverse plane. And this is where I think it's useful to start thinking about the block equations, because there are really good summary equations for how we can describe this magnetization changing in time. So first we can start off with a cross product to describe the precession. In this case, we have two fields, both our static main magnetic field and our oscillating B1 field. And we can separate these out into individual components to look at how the magnetization is changing in time in the multiple directions. And it's much easier in reality to think about these excitation pulses in a rotating reference frame. So now you need to imagine that you are rotating at the Larmoire frequency along with the B1 field. So now the B1 field looks static, and when we look at the net magnetization, it is just making a simple 90-degree rotation relative to our perspective. And so this rotating reference frame is often what we use as a simpler description for the rotation of the magnetization. And we can control exactly how much we tip the magnetization. So here I'm showing two extremes, a small 10-degree flip angle versus a 180-degree inversion pulse. And the way we control this is either by changing the amount of time that we apply our B1 field, or by changing the strength of our B1 field. And again, we can turn this into the rotating reference frame, which is much easier to visualize. So you can see the difference between that small 10-degree flip angle compared to that large 180-degree inversion pulse. And once we've tipped the net magnetization a little bit into the transverse plane, it now has two components, one along the z-axis and one in the xy plane, or the transverse plane. And that component in the transverse plane is rotating again at the Larmoire frequency. And we can use this as an oscillating magnetic field to detect a signal. So that rotation in the transverse plane becomes our MRI signal. That oscillating magnetic field produces a current inside of our receiver coil. And then we can measure a time-varying signal. And it doesn't stay constant over time, it does decay away, which I'll cover more on the next slide. But this decay is called the free induction decay, and this is our first time-varying MRI signal. So as I mentioned, as soon as we turn off the B1 field, the net magnetization wants to return to its equilibrium, and it does that through T1 and T2 relaxation. And I think it's important to point out that T1 and T2 relaxation, although they're occurring at the same time, are totally independent processes. So even though it looks like one is related to the other, they're not. They're both occurring at the same time, but they're different processes on different time scales. So let's start with a flip of the magnetization into the transverse plane with a 90-degree pulse. And then in the longitudinal direction, we have T1 recovery. So the Z or Z magnetization tries to recover to its equilibrium position. It does that with an exponential recovery, and the time constant of that is on the order of seconds. So this T1 recovery is happening on the order of seconds. The T2 describes the decay of signal in the transverse plane. So we start off with a nice coherent signal where our spins are processing coherently, but then over time they interact with each other and create little magnetic field variations that causes them to process at slightly different rates, and they start to dephase very quickly. And so in the transverse plane, our signal decays away with T2. And that exponential decay happens with a time constant that's on the tens or hundreds of milliseconds time scale. And then when we have magnetic field inhomogeneities present, this causes the T2 relaxation to accelerate, and we call that T2 star. And so now our magnetization is decaying away very quickly. And so you can see the comparison of the free induction decay with the T2 versus the T2 star decay. And again, we can include this into our block equations as a really nice way of describing the net magnetization in each axis, and these are just exponential components in the block magnetization, or the block equations. And it's this relaxation that we actually use to generate our image contrast. So even though it seems like a bad thing that we're losing our signal pretty quickly, that's how we can actually generate contrast in our images. So different tissues have different T1 and T2 characterizations, and we can choose the particular timing of our pulse sequences so that we take our picture either when T1 is separated out or T2 is separated out. So now I want to switch gears a little bit and talk about magnetic field gradients and spatial localization. So here I'm showing the first example of a magnetic field gradient. So until now we've been talking about the static magnetic field as having a single value, but actually we can vary the strength of the magnetic field in space. And so importantly, the main magnetic field is still pointing in the z direction. It continues to point in the z direction. It just has a different amplitude at different points in space. So here I'm showing an example along an x direction, where on the left-hand side, the magnetic field is slightly reduced compared to the right-hand side. And to give you a sense of scale, these gradients are usually on the order of 10 millitesla per meter, so very small compared to our 1.5 or 3T scanners that we're used to using. And as we already know, the precessional Larmor frequency is proportional to the magnetic field strength. In this case, now the precessional frequency is varying linearly with the magnetic field gradient. And so if we look at spins across this x-axis, we can see that on the left-hand side they're precessing more slowly, and on the right-hand side they're precessing more quickly. And so this causes dephasing. So if you were to sum up all these spins, obviously they're dephasing over time, but it also allows us to encode spatial information. So in common imaging, we use 3 different gradients and 3 different axes, and there are more complicated ways to use our gradients, but for today I'm just going to stick to the common slice select gradient, phase encoding, and frequency encoding gradients. So we'll start with slice selection. So in this case we have a cylinder, and we want to image a particular slice of that cylinder. So we can apply a gradient field along the length of the cylinder, meaning that the magnetic field is a little bit lower on the left-hand side compared to the right-hand side. And then when we apply our RF pulse, we can specify exactly what transmit bandwidth we want to use to select a particular slice of that cylinder. And the way we select a particular transmit bandwidth is by using a time-varying B1 field. Ideally, we use a sync pulse, because then when we take the Fourier transform, we get a nice sharp slice profile. In reality, we often don't achieve this and have some approximation to this, and so our slice profiles aren't quite this sharp. And once we've selected our slice, we now need to encode the signal within the slice, so we use frequency and phase encoding for this. So we'll talk about frequency encoding first. So again, as I've said before, we can apply a gradient and then cause the precession rate to change across that gradient. So here's an example where on the left-hand side things are moving more slowly than on the right-hand side. And importantly, while we are playing this frequency encoding gradient, we are also acquiring the signal. So we're also measuring the signal from the entire sample. And so if we were to look at the signal coming from each column, you can imagine that it's sine waves with different frequencies. But what we actually measure is a sum of the signal from the entire sample. And so what we actually measure is a combination of these frequencies. And as we all know, to move from a signal that's a sum of sine waves to frequency information, we can use a Fourier transform. And this really easily gives us the profile of the shape. But we still don't have information along that second dimension. And so in order to gain that information, we use phase encoding. And so this is sort of like a preparatory step where we distribute the phase along the vertical dimension before we acquire the signal while varying the frequency along the horizontal dimension. So for example, we can apply a phase encoding gradient, which creates a distribution of phase along the vertical dimension. and then follow that up with a frequency encoding gradient while we're acquiring our signal, which allows us to encode the frequency along that same dimension. And so now if we look at our signal, again, it's made up of multiple frequencies, but in this case, it's slightly lower amplitude because the previous phase encoding had caused some phase dispersion, which reduced our total signal amplitude. And in order to generate an image, we actually have to repeat this phase encoding gradient multiple times to sample along this dimension. And we use the multiple signals that we acquire to fill up our K-space, so this is time-varying signals. And then with a two-dimensional Fourier transform, we can turn that back to frequency space, which tells us about our image. And so in the last few slides, I wanted to go over spin echo and gradient echo before I put it all together. So a spin echo is a combination of a 90-degree pulse and a 180-degree pulse. So starting like we have many times before, we can tip our magnetization into the transverse plane, in this case with a 90-degree flip angle. Then, of course, it decays over time and gives us a free induction decay. But what we can do is apply a 180-degree pulse around the y-axis, and that allows us to switch the phase of the spins that are moving fast and slow. So what was previously fanning out now starts to fan back together. And that produces a signal echo. And the signal echo gives us more information that we can use in our imaging. And the exact amplitude of that signal echo is dependent on T2 relaxation. So there are some effects that we are never able to refocus, but we can refocus influences from the magnetic field inhomogeneities with that 180-degree pulse, so that the echo amplitude is dependent on T2. Gradient echo creates the same concept, creates a signal echo, but it does it using gradient fields alone. So again, we tip our magnetization into the transverse plane. I'm showing a 90-degree flip, but often with gradient echo, we're using smaller flip angles. We then apply a gradient to dephase the signal. And if we switch that gradient direction, suddenly the signal starts to come back together and reform an echo. And in this case, the amplitude of the echo is proportional to T2 star because we haven't been able to reverse the effects of magnetic field inhomogeneity causing additional dephasing. And what we use, most of us, in our day-to-day lives is actually pulse sequences. So we use all of these concepts, but we use them in the form of pulse sequences. And so I wanted to use a spin echo and a gradient echo pulse sequence to just summarize some of the concepts. So we've started with an excitation pulse, which tips the magnetization into the transverse plane that we've talked about over and over today. And at the same time, we're applying a slice select gradient to encode a particular slice of interest. We then apply frequency encoding to get a frequency distribution along one axis. In the case of a spin echo sequence, we use a refocusing pulse to eliminate the effect of magnetic field inhomogeneities. And then while we apply our readout gradient, we acquire signal in the form of an echo. And we use the timing of our pulse sequences to generate T1 and T2 contrast based on when we want to take our picture relative to the decay or recovery of our signal. And I've also used block equations throughout the talk, and I think that these are a really helpful tool when we're trying to understand the net magnetization as it varies in time. And so you can see through this cross product, we can include the precession of the magnetization. We can also include multiple B fields, both the main magnetic field as well as time-varying B1 fields and spatially varying gradients. We can include T1 and T2 relaxation with these exponential time constants. And we can also add more terms. These are very phenomenological, meaning we can add terms to describe different techniques. Things like perfusion, diffusion, chemical exchange can all be included in our block equations, which make them a really powerful tool for modeling our signal. So to summarize, some nuclei have an angular momentum, and a population of spins in a magnetic field will produce a net magnetization. And this magnetization possesses at the Larmoire frequency, which is the same as the nuclear resonant frequency. And then we can use resonance to tip the net magnetization into the transverse plane in order to measure it. As soon as we've tipped it into the plane, it wants to return to its equilibrium state, and it does that using T1 and T2 relaxation, which we can then use to generate image contrast. And we can spatially encode our gradients using magnetic field gradients, or spatially encode our signal using magnetic field gradients throughout this process. So with that, I'll thank all of the many people who have taught this material before I have and taught it to me. And I also wanted to point out a few of the texts that I find particularly helpful as references for you. Thank you.